Hello and welcome to lecture 17 of the course Computational Complexity. In this lecture, we will see an important result in the space complexity theory which is a result by Neil Immerman and Robert Celeb-Seni, right? When they proved that NL is equal to co-NL. Okay? This was proved in 1987, and these two people independently proved the same result, right? So in these times, much like Cook-Levin independently proved from the US or Canada, and the other person in Russia, similarly Neil Immerman was in the western side of things, and Robert Celeb-Seni was in the eastern side of things, and they independently proved the result NL equal to co-NL, right? This is just like Savage's theorem, where we do not have an analogous result in the time complexity classes. This is also a result where we do not have an analogous result, because an analogous result would have been NP equal to co-NP, but unfortunately we do not have that result, right? And so it was believed to be the opposite, that NL and co-NL are distinct classes, but then it was a bit of a surprise when somebody came along and showed that these two classes were the same, right? So let us see how the proof goes, right? So we have already seen in the previous lectures that path is NL complete. So what is path? Path is the problem of given graph G and designated vertices S and T. Is there a path from S to T in the graph G, right? That is the problem path. Now what we will show is that path is in, so we have already seen that path is NL complete, and then we will show that path complement is in NL, right? So the whole proof is going to show that path complement is in NL. So let me, at the beginning itself, let us see why this showing that path complement is in NL is sufficient to show the result that NL is equal to co-NL, right? Okay. So this is because since path is an NL complete language, the complement of path, right, is co-NL complete. So just like we had SAT complement being co-NP complete, path complement is co-NL complete, right? Now if we show that path complement is in NL, which is what we are trying to show, we are actually showing that a co-NL complete language is in NL, which means by reduction, anything that is in co-NL can be accomplished or can be reduced to NL, right? So this implies that anything that is in co-NL can be reduced to NL, or rather co-NL is contained in NL. Okay. So now we want to show NL equal to co-NL. So we have one direction of the proof, and for the other direction, if path complement is in NL, it also implies that path is in co-NL, right? Because anything that is in NL, its complement is in co-NL, right? So the complement of path complement is simply path, and path is an NL complete language. So if that is in co-NL, anything in NL can be reduced to co-NL, right? Because it's an NL complete language. So anything in NL reduces to path, and that is in turn shown to be in co-NL. So this shows that NL is contained in co-NL. So we first showed that path in NL implies co-NL is in NL, and then showed that path is in NL, path complement is in NL implies that NL and co-NL is in NL, is contained in NL, and then we show that path complement is in NL implies that NL is in co-NL. So together these two implications, or these two containments, show that NL is equal to co-NL, right? So all that we have to do is to show that path complement is in NL. This is what we will show for the rest of this lecture, right? Because this is enough, as we have already seen, to show that NL is equal to co-NL, right? So what is path complement? Let us just write it down, right? Path complement, so path is GST such that such that G has a directed path from S to T. So path complement is GST such that G has no directed ST path. So there is no path from S to T in G. So that's a complement, right? So just one small point about complements. Maybe it's a good time to make that point. So whenever I say the complement of a language, we are just taking the opposite. But there are a lot of inputs that are not even conforming to this particular specification, and we usually don't refer to those inputs at all. So it is enough to restrict, because these are usually easy to see that they are not in the correct format. So this can be usually very easily decided. So when I say path complement, I am only talking about inputs in the correct form GST, and since path contains all the GST such that there is an ST path in G, path complement contains all the GST such that there is no ST path in G. Okay. So now to show that path complement is in NL, we want an NL machine to show that there is no path, right? So in a way you want an NL verifiable certificate, right? Just like we had certificates in NP. Now we want an NL verifiable certificate that shows that there is no path from S to T, right? How can somebody produce a certificate that there is no path from this vertex to this vertex? If I want to say that there is a path from this vertex to that vertex, then I can tell you the path and you can verify that this is a correct path, right? So that is okay. However, how can somebody tell you something that you can use to verify that there is no path, right? So that is a challenge here. So that requires some intelligence, some cleverness, some smartness, right? So first we will actually, in this particular part of this lecture, we will answer a slightly different question. The question being, given C, where C is the count of the number of reachable vertices from S, okay? So let us say from S you can reach 10 vertices, right? So C is the number of vertices reachable from S. Now can we show that T is not reachable from S? Okay. So again it's the same problem and exactly the same problem, except that we are giving an extra bit of information, which is the count of reachable vertices from S. Suppose somebody is giving us that. So let me ask you a question. Suppose the count of reachable vertices from S is 1. Now is T reachable? Notice that S is always reachable from itself. So if the number of reachable vertices from S is just 1, that means the only vertex reachable from S is itself. So T is not reachable, right? So suppose we know S has a neighbor, let's say U, and I say that the count of reachable vertices is 2. So then now we know that the reachable vertices are S and U. So these two account for the count given. So that means no other vertex is reachable, right? So this is the idea that we will use. So what we will do is to, if a count of 10 is given, we will show 10 vertices that are reachable from S and actually verify that they are all reachable from S. So we are converting the non-reachability into a reachability problem, right? So we want to show T is not reachable. So instead we will show 10 vertices that are reachable. So, and because we know that there are exactly 10 vertices reachable from S, these must be the 10 vertices. So T cannot be one of these 10 vertices, so T is not reachable, right? So this is how we convert the non-reachability into a reachability problem, or non-reachability verification into verification of reachability, right? So this is the high level idea. Now let us see the details, right? So given G, S, T and C, where C is the count of the vertices reachable from S, we need to verify that T is not reachable, right? So right, perhaps the NL machine, okay, what it can do is to, so now since we have non-determinism, like the cases that I explained was easier cases. So now we want to guess C vertices that are reachable from S, right? So now we have non-determinism. What we can do is that we can guess the C vertices that are reachable from S and verify that they are indeed reachable from S, right? So the NL machine can non-deterministically guess C vertices, okay, and verify. So the non-determinism is used to guess, right, and then verification can be done easily. Verify that they are indeed reachable from S. Okay, and one small point, when we guess C vertices, so these, none of these should be T, right? C vertices, none of which should be T, because if we try to show that if T is one of these vertices, that means that T is reachable, right? So then that means that this is the opposite of what we want to show, right? So all the guessed vertices, none of it should be T, right? So in other words, what we are trying to show is that to show that T is not reachable, right, which is what I have written here in the right side, we will show the existence of C vertices, none of which is T, none of which are T, and that all these vertices are reachable. Okay. So to show that T is not reachable, we will show C vertices that are reachable. Now again, there are implementation details here, right? All this we want to do in non-deterministic log space. We want to show path complement is in NL, right? So we cannot simply guess 10 vertices or something, C vertices, because C could be like, maybe there could be n by 2 vertices reachable from S, and just to write down the n by 2 vertices will require order n space, right? At least order n space. So we cannot have the NL machine just guess all the n by 2 vertices, note them down somewhere, and then go about verifying them. This has to be done in a way so that the space is not the space usage is carefully maintained, right? So how do we do this, right? So what we will do is we will guess a sequence of vertices, and as and when each one of them is guessed to be in guessed to be a vertex that is reachable from S, we will also complete the verification part. So all that we will do is to keep track of the counter, and we will go about choosing these vertices in an order so that we will not end up guessing a vertex 2 times, right? So so each vertex is either picked or not picked. Once it is picked, we will verify that there is a path. If this cannot be verified, then this whole computation thing collapses, because it is not deterministic. We want to show that path complement is in NL, which is not deterministic. All we need to do is to show some way of guessing and correctly verifying. Some sequence of guesses lead to a correct verification. This is all that we need to do, right? So what we have is a counter that iterates through all the vertices. Okay, a counter that iterates through all the vertices at each vertex, right? So the counter could be, let's say, 1 to n if there are n vertices. So each vertex is a number from 1 to n. So when you are at each vertex, the machine can guess whether it is part of a reachable vertex from S or not. So let's say the first vertex is guessed to be reachable. If it is guessed to be reachable, we also guess a path from S to that vertex, S to vertex 1. And once we get a path, we can verify that this path is a correct path. If a vertex, say vertex number 1 is guessed and correctly verified, we increment a count. If anywhere our guesses go wrong, right? So even in guessing whether it is reachable or in verifying, then that whole computation path is rejected. If there is any mismatch anywhere, that whole computation path is rejected. All that we need is some computation path that leads to correct verification. There could be hundreds and thousands of other paths, other computations that could lead to reject. That is okay. All we need is one correct path. When I say path, I meant computation path. So at each instance, we guess whether a vertex is reachable. Let's say vertex 10 is reachable, we correctly guess a path from S to that vertex 10 and verify it, and then the counter is incremented. If we cannot correctly verify it, or So that can happen due to two reasons: either the guessed path is incorrect, or the vertex is also if the vertex is reachable but the path is incorrect, or the vertex itself is unreachable. Whatever be the case, the entire computation is rejected, is terminated. Okay, but if there will be a correct set of since we know C, the number of vertices that are reachable, there will be a sequence of guesses that will lead to correctly identifying these C vertices. Okay. So and since T is not reachable, if T is not reachable, we will correctly identify these C vertices, and none of it will be T, and we will accept, because we need to show that T is not reachable. So if T is not reachable, that leads to accept, right? This is what we will do. This is a high level idea. So let me just say it once again. So I don't I'll erase this part. So this is a small bit. So D is the count of the vertices reachable from S. We assign it to 0, right? So I am talking about item number 1 here. We initialize to 0, and for each vertex U in the graph, we either select it to be a reachable or we select it to be an unreachable vertex. If it is selected to be a reachable vertex, then we call the function checkpath of GSUV. Checkpath, what it does, I will just briefly explain now, and later we will see it in detail. It will check whether there is a path from S to U that of length at most V, size of V. This is what it does. So if it is a vertex that is reachable, then we will guess it correctly, and we will call the function. And if at any point the guessed vertex, if U is guessed to be reachable, T is guessed to be reachable, then the whole computation path is rejected, because T is something that we do not want to reach, right? If at any point T is found to be reachable, we do not proceed with that computation. And for every vertex that is correctly verified to be reachable, we increment D, right? At the end, we see if we have not rejected the computation, right? Then we see what is the count. Is the count equal to the actual count that is given to us, which is C? So recall, we are given G, S, T, and the actual count of vertices reachable from S, which is C. So we check whether we guessed C vertices that are reachable from S. If we guessed the C vertices that are reachable from S, none of it being T, we accept. Otherwise, we reject. Right? So if T is not reachable, this will accept exactly when T is not reachable, and we are able to guess the vertices that are not that are the vertices reachable from S. Because if T is reachable, then the count of vertices reachable from S will include T, and the algorithm will break, because we also check that none of the vertices reachable are equal to T. Okay. So what is the space usage here? Let us see what is required to be saved here. D is a counter that needs to be saved, and U is a counter, right? U is a vertex. You need to check for each vertex U equal 1, 2, 3. So that's also a counter. So D and U are the things to be that occupy space. We also call the function here checkpath. So the checkpath will use some space, but that we will worry about when we actually see the function checkpath. Right? So right now let us not worry about that, because we have already seen that calling a function, if a program, if a machine runs in NL space or logarithmic space, and you can always make a function call, that function call may also be in NL space, and you can always do that. This we have already seen, right? At the beginning, when we showed the why the log space reductions make sense. So you can combine these, but anyway, the checkpath function we will see very soon. So the only things that we need to save here are U and D. right? D is a counter of length at most C, so of C, which is at most C, and C is a number less than the number of vertices in the graph, which is less than n. U is also a counter that will go up to at most n. So both of them are numbers at most n, so can be represented in O log n bits. So the total space usage is O log n, right? So just to illustrate, right? So suppose this is S and C is 8, so which means there are 8 vertices reachable from S, including itself, right? So these 8 vertices are guessed, right? And we correctly guess these 8 vertices and verify the paths. So now this means that T is not reachable because these are exactly the set of vertices that are reachable from S, right? So what we are doing here is to, like, first we guess the list of 8 vertices reachable from S, right? And this is not done in a collective manner. We not guess all the vertices reachable. We just do that one by one, right? And then for each such vertex V that is guessed to be reachable, right, we guess the path from S to V. And this is not done in the code that we showed right here because that is being done by the function checkPath. Okay. So here what we do is we one by one we guess each vertex to be reachable or not reachable. If it is reachable, we guess the path. And if any of these doesn't work out, like either we guess an unreachable vertex to be reachable, or a reachable vertex to be unreachable, or T to be reachable, or we guess everything correctly but one of the paths from S to a vertex V is incorrectly guessed. Anything of this happens, that computation path is cancelled. All that we need is some computation path gets all the guesses correct, and that is enough for us. So then we can verify that T is indeed not reachable from S by guessing the correct set of vertices that are reachable from S. Now what remains is to see the function checkPath. How do we check that a vertex, there is a path from S to U in V steps? Okay. So checkPath checks if there is a path from S to U in the graph G with at most V edges. Okay. So again, I have already kind of explained what it does, but so this is a very simple subroutine. There is not much high level ideas here. All we do is something like this. So suppose S is this and U is this. We just guess a sequence of vertices. Let's say W1, W2, and something W1, W10, W6, right? Something like that. And we keep moving ahead, and we check if we reach U at any point. Right? So what we do is, we guess a sequence of vertices. Let's say W1, W10, something. So for each successive pair, we check whether it forms an edge. Okay. So what happens is initially we call S to be equal to W prime, and we guess a W. So let's say the guess W is W1, and then check whether there is an edge from W to W1, W prime to W. So now in this case S is W prime, W1 is W, so there is an edge, so fine. Now what we do is we rename W to be W prime. Not just that, we also increment a counter. So now we have verified one edge, we increment a counter to 1. So the counter here is, the counter that is used here is J. So J is equal to 1 now. Now this is W prime, we guess another W, right? So let's say this W10 is guessed. Check whether there is an edge from W prime to W. So W1 to W10. Indeed there is an edge. So J is incremented to 2, and W is again renamed to be W prime. Now let's say we guessed W to be, let's say, some other vertex, let's say some W15 from which to which there is no edge. In this case, we will check whether there is an edge and we will not see an edge. So this computation path gets rejected. This entire computation goes. But the point is, if there is a path from S to U, there will be a sequence of guesses that will help us verify that U is reachable from S. Finally, why do we have the counter here? That is because we know that we are checking whether the path is of length at most k. Right? Check path is called for GSUK, whether there is a path from S to U in G of length at most k. Right? So here we used at most, here we used V, but we will see that we will need this for other variables. That's why it is given as an argument. So we are trying to see whether there is a path of length at most k. In fact, there is a small typo here. No, there is no typo here. Sorry. We non-deterministically guess the next vertex and keep moving ahead. If there is a path of length at most k, we will find it. So if the counter, so reject if the so this part is written for size v, k is equal to size v. So maybe I'll just modify it slightly. So what is check path GSUK, and reject if counter becomes greater than k. So when counter becomes greater than k means we are exceeding the limit, so we will stop. Right. So this is all that we do. If we keep progressing this pointers W prime ahead with incrementing the counter, and we accept if the counter J does not cross k and W prime reaches the target destination U. So if at any point W prime or W is equal to U, then we accept. Otherwise, we reject. So there are two things checked here. Whenever W is guessed, we reject if there is no edge from W prime to W, and or if we also and if W is not equal to W prime. If W is equal to W prime, then it is fine. That leads to an accept, right? So basically, this is the algorithm to check whether there is a path from S to U of length at most k. So you guess at W, we reject if W prime and W do not form an edge and W prime is not equal to W, right? So in other words, this is using this De Morgan's laws. It is nothing but W prime W is an edge, or W is W prime, right? This whole thing, the negation of this whole thing is what we have. So we are okay if either of this is the case. We reject if the opposite of this happens, right? The complement. And we accept if we reach W equal to U. Otherwise, we reject when the count of the steps crosses k. So what are the things that we need to keep track here? The things that we need to keep track is W prime, W, which are variables, either of and then J, which is the count. The count will be less than at most the number of vertices n, and even for W and W prime, these are labels of length, which can be at most n if you use the numbers to name the vertices. Even if you use something else, it will be something similar, and each one of them is at most n and can be written in a log n space register or memory location. So each of them require log n space. So total we need O log n space. There are constant number of items that require log n space. Again, we use non-determinism but are in log n space. So we have seen, given a count of number of vertices reachable from S, how to verify that T is not reachable from S, right? By guessing a set of vertices reachable and then verifying that they are indeed reachable, and none of these vertices are T, we verify that we verify that T is not reachable. Right? So now the question remains, we started with this assumption, how do we, that the number of vertices reachable is given, but now how do we compute? The original problem statement did not have this C provided to us. Now how do we estimate C, or how do we come up with C using a non-deterministic log space machine? So that part I think I will defer to the next lecture video, just for ease of keeping the videos short. Right. So just to summarize here, we wanted to verify that T is not reachable from S. So we saw how to do that if we are given the count of vertices that are reachable from S. If we are given the count, we guess, if C is the count and C is 10, we guess 10 vertices reachable from S, none of which is equal to T. We just guess them and verify that they are reachable. So this is what we have seen so far. And in the next video, next lecture video, I will explain how to come up with the number of vertices reachable from S in non-deterministic log space.